Okay, so you sent in a bunch of stuff about thermodynamics, and it seems like you want to really get down into it. Not just like the basics, but like how it works and why it matters and
Yeah.
how we see it in our lives. So
Well, okay.
we're going to unpack the 4 laws of thermodynamics
Yeah.
and look at some real-world examples. Maybe even tackle the big question: could a perpetual motion machine actually exist?
Oh, I like where this is going.
But first, thermodynamics is essentially the study of heat and energy,
Uh,
how they transform and move around.
exactly. And it's like surprisingly relevant to pretty much everything
Huh.
around us.
Okay, so let's dive into the laws. First up is the granddaddy of them all,
Okay.
the first law of thermodynamics. Energy cannot be created or destroyed, only transformed.
I feel like I kind of get it, but it's almost too simple.
Yeah, it is simple, but it has like huge implications. Think about it. Every time you drive your car,
Okay.
you're literally converting the chemical energy stored in gasoline into motion.
Yeah.
And that energy doesn't just disappear.
It gets transformed into heat, sound, even the tiny vibrations in the road.
Wow, so it's like this never-ending
Yeah.
game of energy swap.
Yeah, totally.
Okay, so then we have the second law.
Okay.
This one says heat flows from hot to cold,
Right.
which explains why my ice cream melts on a hot day.
Yes.
Right? But I remember something about entropy being involved here.
Yes, entropy is a bit more complex.
Yes.
It's about the tendency for things to become more disordered over time.
Okay.
Think about a tidy room versus a messy one.
Uh,
There's only one way for a room to be perfectly tidy, but countless ways for it to be messy.
right.
So entropy is always increasing, ice melting.
Yeah.
That's a more ordered state becoming less ordered.
So is this saying that the whole universe is destined to become one giant messy room?
Well, kind of. The universe tends towards higher entropy. It's fascinating because it gives us the arrow of time.
Hmm.
Things move from order to disorder, from past to future.
Whoa. Okay, on to the third law.
All right.
This one says absolute zero is unattainable. So like there's a limit to how cold things can get.
Exactly. Absolute zero, Natick's 273.15 degrees Celsius, is the point where theoretically all molecular motion would stop. But there's catch. Even at extremely low temperatures, there's this weird quantum phenomenon called zero-point energy
Okay.
that prevents particles from completely stopping.
Hmm.
We've gotten really close, but absolute zero remains this ultimate, unreachable limit.
That's wild. It's like the universe is saying, nope, you can't go that cold.
Exactly.
Okay, last but not least, we have the zeroth law. This one sounds kind of out of place.
It does, right?
Yeah.
They basically realized they needed this fundamental law after the others were established.
Okay.
The zeroth law defines thermal equilibrium.
Okay.
Imagine you have a thermometer,
Okay.
a glass of water, and a hot cup of coffee.
Right.
If the thermometer and the water are at the same temperature,
There.
and the water and the coffee are at the same temperature, then the thermometer and the coffee must also be at the same temperature. It establishes this common point of reference.
Uh-huh, got it. So it's less about a specific process
Yeah.
and more about setting the stage
Yeah.
for understanding how systems reach a thermal balance.
Exactly.
Okay, so we've covered the laws. But how about those real-world applications? You mentioned perpetual motion machines earlier.
Ah, the holy grail of those who want to break the laws of physics.
Right.
But the first and second laws make it clear that perpetual motion is impossible. You
Yeah.
can't create energy from nothing.
Right.
And you'll always lose some energy to entropy, usually as heat.
Bummer. Okay, but what about stuff we do use every day?
Hmm.
Like my car engine.
Internal combustion engines are incredible feats of engineering. You've got controlled explosions happening thousands of times per minute, converting chemical energy into mechanical force. And different engines, like diesel or jet engines, operate at different temperatures and pressures, which influences their efficiency.
It's mind-blowing how much thermodynamics goes into something we take for granted. What about refrigerators? How do those little boxes manage to defy the natural flow of heat?
They do it by cleverly exploiting the second law. Refrigerators use a special fluid called a refrigerant,
Okay.
which cycles through different states, liquid and gas, to absorb heat from the inside and release it outside. It's like a tiny controlled heat pump powered by electricity.
So it's like a heat wrangler in my kitchen.
Exactly.
Finally, let's talk about the elephant in the room.
Okay.
Climate change. How does thermodynamics fit in here?
Well, think of the Earth as a giant thermodynamic system.
Okay.
We have this delicate balance of energy coming in from the sun and radiating back out into space.
Right.
But the atmosphere, with its greenhouse gases, traps some of that outgoing heat. which affects the Earth's energy
Right,
budget.
and we're messing with that balance
Yeah.
by pumping more greenhouse gases into the atmosphere,
Exactly.
which leads to rising temperatures and all the climate chaos we're seeing.
Exactly. Thermodynamics helps us understand how that energy flow is changing and why even small changes in temperature can have massive effects on the planet.
Wow, so in a way, thermodynamics is like the ultimate cosmic rulebook.
Yeah.
It governs everything from the tiniest atoms to the fate of the entire universe.
Exactly. And the coolest thing, it leaves us with more questions than answers.
Oh,
If energy can't be created or destroyed, where did all the energy in the universe come from in the first place? And knowing that entropy always increases, does that mean the universe is destined to end? In a state of maximum disorder, a heat death?
mind officially blown. So you're telling me that understanding how my coffee cools down can lead me to pondering the fate of the universe.
That's the beauty of thermodynamics.